Having studied the product rule, we're now going to take a look at the quotient rule. So, as its name implies, this rule is going to tell us how to differentiate the quotient of two functions. So the quotient rule states that if f of x and g of x are two differentiable functions, then the quotient f divided by g will be differentiable whenever g does not equal 0, and the derivative of f divided by g is given by this rule right here. So it's going to be g times the derivative of f minus f times the derivative of g divided by g squared. And you can think of this rule as stating, if we start in the bottom of our fraction here, we go bottom term times derivative of the top, that's right here, minus the top times the derivative of the bottom term divided by the bottom squared. And that's how we differentiate the quotient of two functions. Now, once again, just like the product rule, you have to be careful. The derivative of the quotient of two functions is not the derivative of f over the derivative of g. It's this up here. This is how we have to differentiate the quotient of two functions. So it is not this right here. So please do not differentiate the quotient of two functions by taking the derivative of the top divided by the derivative of the bottom. That is not how we do it. We have to follow this rule. So what we're going to do now is just take a look at a few examples. So our first example here is we just want to differentiate this function, x squared plus 3x plus 5 divided by x squared plus 1. And up here we have the quotient rule stated so that we can see how we're going to follow it. So for the derivative of this function, df dx, is going to be, we start in the bottom. It's going to be the bottom term times the derivative of the top term. That's going to be in the numerator of our fraction. So it's going to be and then minus the top term times the derivative of the bottom. And then we have to divide by the bottom term squared. And now what we have to do is just clean everything up. We have to evaluate the derivative of x squared plus 3x plus 5, the derivative of x squared plus 1, and then that's going to be our answer. And then we can do any simplification that's required. So our derivative then is and this is our answer. Now we can simplify this a bit. We can FOIL this out, distribute the 2x, combine like terms in the numerator. Sometimes you'll see some cancellation occurring with what's left in the denominator down here. Sometimes. And so let's do that. So this right here is simply these two terms FOILed out, and then minus. And these terms here come from distributing the 2x among the x squared plus 3x plus 5, and then distributing the minus. And then we have to divide by. And now we can clean up the numerator a bit. Notice we do have some cancellation. And we can combine the 3x squared with the negative 6x squared, the 2x with the negative 10x, and we end up with this. And that's all the further that we can simplify it. You can factor the numerator, but that's really not necessary. It could be factored like this. But this isn't really necessary, although you may see some textbooks, if you look up an answer in the back, there's a chance that they might factor it like this. But this answer's fine right here. Alright, and so that's how we apply the quotient rule to this problem. Let's take a look at two more. So here we want to take the derivative of the sine x divided by x squared. So applying the quotient rule up here, we are going to go bottom times derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. And just realize that x squared squared is x to the fourth power by properties of exponents. And now we just have to differentiate and do any cleanup work. And notice we can do some cleanup here. We can cancel an x in the denominator here with an x here and here in the numerator. So we can do this. That would become a 3. This x would totally cancel, and this exponent here would become a 1. And then we end up with and that's our answer. So that's the derivative of sine x divided by x squared, and we really can't simplify that any further. Let's take a look at another one. So here we want to take the derivative of cosine x plus x cubed divided by 5. Now I put this one in here for a reason, because sometimes you want to recognize when you don't need to use the quotient rule. The quotient rule is rather cumbersome, so if you don't have to use it, then don't use it. In this case, recognize that you can actually write this as 1/5 times cosine x plus x cubed. So then we don't have to use the quotient rule at all. So even though this function is written as the quotient of two terms, just recognize that because you have a constant in the denominator, you can actually pull that out and just treat it as a constant times the numerator, and then you don't have to use the quotient rule. So then the derivative of this just becomes just recognizing that the derivative of cosine is negative sine, and then if you'd like, you can distribute the 1/5 through. And there's our derivative. Negative 1/5 sine x plus 3/5 x squared. Now let's take a look at a proof. Now here we're going to prove the power rule in the case when n is a negative integer. If you remember, we only proved the power rule when n was a positive integer. But now that we have the quotient rule at our disposal, we can prove the power rule is true when n is a negative integer as well. Now when we do this proof, let's remember two things here. Let's note that the absolute value of n is negative n. That's for n, a negative integer. For example, the absolute value of negative 3 is negative of negative 3, because that gives you back positive 3, right? And let's also note that x to the nth power is then going to be 1 over x to the absolute value of n. For example, if I look at x to the negative 2, in this case n would be negative 2, that's going to be 1 over x squared, right? Which is, of course, 1 over x to the absolute value of negative 2. All right, so keep this in mind as we're going through our proof. Now, let's start with, we want to evaluate the derivative of x to the n. And so using this fact here, you can write it like that. And now let's use the quotient rule on this. So we're going to go bottom times derivative of the top But the derivative of 1 is just 0, right? That's a constant. So this term is going to disappear. Minus top times derivative of the bottom. Just have to subtract 1 from the exponent there, drop the absolute value n down, and then divided by the bottom squared. And then we can clean this up a little bit. This term, of course, is 0, so that just goes away, and we end up with and now we can just subtract 2 times absolute value n from this exponent up here using properties of exponents. Remember, x to the a over x to the b is x to the a minus b, right? Okay, using that fact, what we have then down here is and then we can clean this up as now negative n minus 2 times, not negative n, absolute value n minus 2 times absolute value n, that's just going to be negative absolute value n minus 1. And then keep in mind negative absolute value n, that's just going to be n in this case. Just to note that, go up here and notice up here that we have this rule, right? And that can actually be rewritten as negative absolute value n equals n, right? Okay, so we replace the negative absolute value n with n, and we get, well, that looks exactly like the power rule. And remember, n is now a negative integer. So we have now proven the power rule for the case when n is a negative integer, as well as a positive integer, which we had proven earlier. All right, and that does it for our discussion of the quotient rule.